Sorry with ending the last video with an Boy, that was a great way to end it, but I wasn't gonna get rid of the whole thing. So I'm talking about this EA over RT ratio, and that's in the exponential factor in the Arrhenius equation. And so I'd like to just talk about, first of all, what is this RT, So can I tell you anything to shed any light on this? So first of all, we know what EA is, right? EA is that required activation energy. And this sometimes can be actually very significant. So what is RT then? So RT, okay, so you could see the T, the temperature is in here. And we know that as the temperature goes up, that molecules have more kinetic energy. They have more energy, basically. This kinetic energy can be used to break bonds or to stretch bonds. And so as the temperature goes up and molecules have more of this kinetic energy, they are able to acquire the needed energy to go over the barrier in the reaction, okay? So RT can be thought of as a measure in some way, some kind of measure of the available energy that a molecule has, or that molecules have. And we know that not all molecules have the same energy in a sample, right? In a sample of gases, we certainly know they're all moving with different speeds, and they have an average energy. But what we do know is as the temperature goes up, the available energy goes up. So as T increases, available, oh, I can't spell anymore. So let's think about this ratio then, EA over RT. So this is the needed energy divided by the available energy. And something we can certainly say for sure is that if the needed energy is greater by a lot than the available energy, well, there's going to be few molecules that will have the needed energy to go over the barrier. And what's that going to do to the rate? What's going to happen to the rate constant, K, will be small. Okay? On the other hand, if the activation energy is much smaller than RT, the available energy, then lots of molecules will have the activation energy, okay? And then the rate, or the rate constant, will be fast, or be large, I should say. Okay, so how does this work with the graph? Because I spent so long working on, telling you about that graph. I really would like to use it and show you something. So here's that graph. Here's EA over RT, and here's e to the minus EA over RT. And we know the curve looks like this, and this maximum is 1 here. Okay? So as we go in this direction along this graph, EA increases. So as EA increases, the number of molecules that have that energy goes down, right? So as EA goes up, e to the minus EA over RT goes down, fewer molecules have the needed energy. But we can also think about using this graph to see what happens as the temperature changes. So again, we have e to the minus EA over RT going like this, We have EA over RT. Now, as the temperature increases, which way are we going on this curve? Right, temperature, notice here, is in the denominator. So as T goes up, EA over RT goes down. So we're kind of going in this direction. So we will really be going up the curve. So this is as the temperature increases, EA over RT is going down. So we're moving in this direction. So as the temperature increases, the fraction of molecules with the needed energy goes up because we're going in this direction and the graph is going up. Let me fix that. So this graph is great because it tells you what's happening to the fraction of molecules. That's what this really means, with the needed energy, EA. It tells you what happens to that fraction. As EA goes up, we go this way. As T goes up, we go that way. So as EA goes up, we get fewer and fewer molecules that have the required energy. But as T goes up, the opposite is true, and we're going this way on the curve, and we get more and more molecules that will have that required energy. So this is a nice graph, you know, and it makes sense, right? Because at higher temperatures, more molecules have the needed activation energy, and so K will be larger. At lower temperatures, fewer molecules have the needed activation energy, and so the K is smaller. Now, I really don't care if you understand this way or by using the graph and understanding the mathematics. I just want you to understand that that first of all, as the energy increases, as the activation energy goes up, K goes down, right? And as the activation energy goes down, K goes up. So this is the first fundamental thing that you should understand. If you have more energy that's needed, fewer molecules are going to have that energy, the rate constant will go down. If you have a lower activation energy that's needed, you'll have a lot more molecules that'll have that energy, the rate constant will go up. So that's the first thing you need to understand. And this is the second thing you need to understand here, this whole parentheses here, which is the role of temperature. When the temperature goes up, more molecules have that needed energy, and the K will be bigger, and etc. Vice versa, I would say, for the lower temperature. So I don't care if you like to understand it in terms of the exponential graph. I think that's wonderful if you like math that way. But if you don't, what's really important is that you just grasp the theory of it, you know, and you know which way it's going to work. I thought that, you know, since I'm talking about exponential functions and since we're all going through this coronavirus stuff, that I would tell you that this function that I looked at before, remember when I was looking at 3 to the x. So when you think about how the virus spreads, there's something called an R number, which is one of the things that scientists are trying to find out about this virus. And this R number is how many people on average does one person with the virus spread the virus to. Okay? And if that, so that number, I've read various things, and scientists think that number may be like 2 or 3 or something like that. Like if every person spreads the virus to 3 other people, for example. Well, this function here that I talked about earlier would actually describe how the cases change. So let me explain this. So if, let's say the R number is equal to 3, okay? And let's look at the function 3 to the x. Okay, if x is equal to 0, so this would be like patient 0. 3 to the 0, that's one patient with coronavirus. Okay. Now, if that one person transfers that virus to 3 other people, so now we have 3 people that that person has transferred the virus to. That means now, so here we had one person, now we have 3 people, but now each of those is going to transfer the virus to 3 more people. And guess how many we have? We have 9. We have 3 squared, okay? And now we go one more step, which I really don't have room to show, but it would be each of these would give 3 more. Okay, so that's 3, 3, 3, 3, 3, 3, 3, 3, 3. 3 times 9, which is 27, which is 3 squared. So this function 3 to the x versus x would be how the number of viral cases with the virus increases with each transfer from like the first person to the second this is like the first generation, the second generation, the third generation. And it increases so rapidly, which is what's meant by exponential increase in virus cases. So if the R number weren't 3, like if the R number were 2, then this wouldn't be quite as rapid, right? Then you'd get 1 giving 2 and 2 giving 4. It's still considered exponential, but it's that R number that influences exactly how this is going to go. So here we have 1, 2, 4, 8, and then it'll be 16, etc. If R is equal to 3, it's going to be 1, 3, 9, 27. What's 27 times 3? Whatever that is, like 75, 81, I guess. Okay. So anyway, just thought I'd mention that because there's all this talk about exponential growth and everything out there, and since we're covering this, I thought I would just tell you a little bit about that. Okay, there's one other thing I wanted to tell you about this Arrhenius equation, and it has to do with what you were going to do in lab the second week of the kinetics. Is a 2-part lab, and in the second week of the kinetics lab, and we're preparing a dry lab for you to do, so you will end up doing this. What we were going to be studying then would be the temperature dependence. So in the first week, you will find the rate constant K for a particular reaction at 25 degrees C. You'd also find the rate law. Okay, the second week is the temperature dependence of K. So you would have been running reactions at different temperatures. And what you can get from looking at the temperature dependence of the rate constant, you can actually get data that will allow you to figure out what the activation energy and the pre-exponential factor are. So I'm going to show you how that's done. So here we have this, exponential, well, I have to put the pre-exponential factor. We have A e to the minus EA over RT. I hope that's a little less mysterious now. And what happens if I take the natural logarithm of both sides? Okay, now here I can use the rule of logs that says that the log of AB is the log of A plus the log of B. So that makes this the log of A plus the log of e to the minus EA over RT. And so now I can take the log of e to the minus EA over RT, but remember, if you remember from math, that the natural log and the